I've got a bit of a story to tell here. First, a bit of background. As you said, I'm Scott Laird. This is based on a bunch of work done at Figma during 2024. If you're not familiar with Figma, they make tools for designers. A bunch of products that you use were probably first sketched out with Figma, apps, websites. I think my car's dashboard was designed with Figma. And just like in Google Docs, users rapidly end up with folders full of drafts, one-off projects, sketches, and finding the document you're looking for gets tricky. So document search is important to Figma users. I started working with Figma's internal document search team in 2024 to help fix latency, scaling, and reliability issues. And they were really excited when I joined, because prior to Figma, I'd spent 17 years at Google as an SRE. Surely I knew all about search. Yeah, so I had this long arc of all sorts of different projects over the years, and I know nothing about search. I'd never touched search. I mean, everybody knows a little bit about search. Latency is critical, relevancy is nice. We probably shouldn't give users errors. Yeah, no clue. So Figma search people were all excited. Ooh, do you know all about? No. Well, how about? And yeah, no, not that either. It ended up being such a sad discussion. So much hope dashed, the poor people. Anyway, Figma had an elastic backed search feature since really early in the company's existence, but it received kind of a lack of love for a few years. It was running a 3-year-old version of Elasticsearch on AWS, and it had a reputation internally for being kind of flaky in a bunch of ways. In general, it didn't give customers or on calls the experience that we really wanted to give them. So the company had started adding a bunch of people to search recently and had big plans for making it better. So, what was wrong? The usual things. It was frequently really slow. Sometimes customers would see multi-second latency for searches. Not real happy. Sometimes the whole service would grind to a halt based on surprisingly small changes in traffic. We were spending a ton of money on search, and it didn't really feel like we were getting our value out of this whole thing. But worst of all, we didn't really understand why it was slow or flaky or expensive. Almost everyone involved was new to search. The whole team was still learning. On the plus side, we had an amazing team, especially the search relevance side, which is really unusual. We had data scientists going through all of our stuff, and we understood how our search results served our users once they finally showed up. So fortunately, there was already a bunch of work going on to fix things. They'd started replacing our ancient version of Elasticsearch with a managed OpenSearch instance on AWS using what had been the newest version of OpenSearch. If you're not familiar, OpenSearch is a fork of Elasticsearch that mostly Amazon created when Elastic changed their license. Pretty much everything in the talk applies to both of them. Anyway, Figma was bringing in some people to help, and I was supposed to be one of the experts. Except I knew less about Elasticsearch than I did about Google Search. I'd fired up at home a couple times to look at some logs and watched it descend into madness over a few weeks. I had no idea what I was doing. And the team understood that I was far from an expert on search after the initial introduction. Whatever, we've got a job to do. Let's get to work and fix this. Which gets to the heart of what this talk is really about. How do you approach a problem as an SRE when you barely know where to start? And I decided to do something that felt kind of weird, because it's the sort of thing that as SREs we always think we should be doing, but almost never seem to do much of it. I ended up using science. Not that much glassware and more coffee cups. But the first step of this whole process was to try to figure out what we knew and what we didn't know. Where were we even starting? We had tons of dashboards, literally hundreds of graphs. Some of the graphs had hundreds of lines, because more is better. We had alerting. We had customers sending us politely worded, well-designed hate mail. We had suspicions about what was wrong, but we didn't really know anything for sure. Sure, we could have just thrown more CPU and RAM and servers at the problem, and maybe that would have helped, but we wouldn't even have known if it did. It might have even made the problem worse. So, we're SREs. We start with monitoring. We try to answer the most basic, most critical questions. For now, I didn't care about document ingestion latency or JVM GC stats or rollout delays. I just wanted to know 3 things. How many customer searches do we do per second? How long do they take? And how many errors do we serve? The most basic, non-complicated questions for any service. We had answers to all of these in our monitoring, spread across 2 different dashboards, None of them were in the top screen full of either dashboard. None of them were even close to each other on the dashboard. But worst, all of them were wrong. And they had to be wrong because we had multiple graphs that answered each question and they all disagreed with each other, sometimes by a factor of 100 or more. Science, right? So the first step was to figure out, what are the right values for these metrics. We can look at all the different sources of truth, kind of agree with what differs. We can check out our measurements, see what we actually know. Then we can figure out which bits are most accurate, which are most likely to be true, and work from there. And at this point, I just wanted to gather some data to figure out how broken things really were. I mean, search had a bit of a reputation internally, but it mostly worked for me. I just wanted to understand what was happening, not why, not the causes, just how heavily used it was, how slow it was, and when did we serve errors? Welcome to middle school science class in the scientific method. We're going to gather some data, form some hypotheses, test them, publish some results, and iterate. First, we're going to gather some data. Let's start with our search rate. It seems easy enough. How many searches do we do per second? We had data from OpenSearch that said how many searches it was performing for us. You'd expect that to be accurate. Are we performing searches without it knowing about them? We had data from our front end saying how many queries hit our search API. We control the code. It should be fairly accurate. We should be able to understand it. The two numbers were a factor of 500 apart. OpenSearch thought it was doing way more searches than our front end. Okay, fine. Query rate is hard. Maybe we'll start somewhere else. Let's try latency. OpenSearch said its mean latency was 8 milliseconds. Mean, what a fascinating way to look at latency. We had many terabytes of data split up into hundreds of shards. That seems impressively and improbably fast to get an answer back in 8 milliseconds. But fine. Our front end was claiming a P99 latency of 1 second, but it did a bunch of extra work besides calling OpenSearch. A bunch of message checking, how much time did we spend on that? We didn't have a metric. We didn't even know how much of that time was spent processing versus calling OpenSearch. All we knew is we had 8 milliseconds on one side and 1,000 milliseconds on the other. Science, right. So, when in doubt, add more instrumentation. We added a bunch of extra trace spans and metrics. We wrapped a bunch of calls to OpenSearch's API in histograms. We traced everything we could. We ran down all the existing metrics to make sure they actually measured the thing they were supposed to. Most of them did. We also dug into the fun that's AWS's CloudWatch. After 30 minutes, we determined that while our mean query time was 8 milliseconds, AWS did actually know the P99 for queries. It was 9 milliseconds, sometimes 10. So this isn't helping us. At the same time, our new code, we finally knew that our outgoing latency to OpenSearch was 200 to 400 milliseconds, depending on the time of day and load and so forth. And looking at our traces, we saw an absolute minimum of 40 milliseconds. So OpenSearch, worst case is maybe 10 milliseconds. Our best case is 40 milliseconds. Are we accidentally calling OpenSearch on the wrong side of the continent or something? So we kept adding more instrumentation to our code, and a few patterns started to appear. We were fast on nights and weekends, slow at peak times, but when we looked at the data from OpenSearch, it really had no correlation. It was like we weren't even measuring the same thing. Right, so you need to know what you're measuring. And I'm sure there's a bunch of people in the crowd shaking their heads at this point and saying, he's right, he really doesn't know how Elasticsearch works. But for the rest of you, let me walk you through a quick query. I'll note that I was hired to do SRE things, not graphic designer things. So the app here is our code. The rest of it is OpenSearch. So we have, in this case, a coordinator node that's sort of the front end for the API. We're going to send it something, and it's going to talk to a bunch of worker nodes. Each of the worker nodes have some number of shards of our data on local-ish disk. So our app sends an API request. Let's search for food to the coordinator node. It does some checking and query optimization, and then sends subqueries off to each of the worker nodes. And to be clear, the outbound queries go to each data shard, not just each node. If we have 200 backend nodes and 200 shards, there are 200 outbound queries, not 20. And the shards are distributed in some pattern over the nodes with some amount of redundancy. Each worker node will do a search, respond with an answer like, the top 70 results from my shard are, That goes back to the coordinator. The coordinator takes all of those, sorts them, merges them, and then goes back and asks for more information about the documents that got the highest score. It's like, yeah, you give me the document ID, now can you actually give me a snippet I can return to the user, so forth. Those come back, the coordinator bundles up the answer, sends a response back to your app. So the reason I'm explaining all this is we discovered Open or Elasticsearch's metrics are all per shard, all of them. Every single metric that we had from OpenSearch's side measured the per shard latency, per shard errors, per shard query rate. It's not per API request. It's not per node. It's per shard. How much time does the coordinator node spend merging partial results? How much does long tail latency impact things? Are there queuing delays? Dunno, it doesn't measure that. Surely we're doing this wrong. I mean, this seems surprising for a mature product. So we went off to read the OpenSearch docs. They're terrible, completely unhelpful. So we read the Elasticsearch docs, way better, still completely unhelpful. Opened some support tickets with our AWS support folks. Let's just say they weren't monitoring experts. Then we talked to a bunch of OpenSearch devs at AWS who all looked kind of shifty and guilty and said that it's fixing it's on their roadmap. Okay, so since we can't really trust OpenSearch's metrics, we decided we just have to concentrate on front-end metrics. What do we see from our side? So we wrote some probers to talk to OpenSearch. We added some extra tracing data. We aggressively wrapped every single API call in our monitoring. And slowly, we started to make sense of things. We started getting self-consistent data. We had reasons to believe it was true. I mean, maybe things weren't that bad. I mean, okay, we still had 1 second latency. Inquiry still slow to a crawl sometimes, and we're still paying through the nose. But, and this is the critical bit, we could finally make changes and tell if they helped. So, I mean, now we can fix things. So, I mean, time to start asking questions. We've made it to the past the gathering data point of things. We can start kind of heading towards hypotheses. And, could we optimize our queries to run faster? Are we doing the OpenSearch equivalent of full table scans all the time? Or are they relatively efficient? If our P99 latency is 400 milliseconds and search front-end API latency was 1 second, where's the rest of the time going? Are there OpenSearch config flags and changes we can make that would help? Could we throw hardware at it profitably? Would changing AWS OpenSearch instance types help? Would upgrading the newer versions of OpenSearch help? And you'll notice a lot of these questions were, if we changed X, what would happen? And this was kind of tricky because we didn't have a good way to test this. Yeah, so anyway, the question is, how do we benchmark a bunch of test queries against OpenSearch? I mean, surely there's got to be a tool for this. I wonder what it's called. Oh, look, OpenSearch Benchmark, part of the OpenSearch project. Took a wild guess and said, maybe this is what we're looking for. Right here on GitHub, part of their project, been around forever, forked off from an Elasticsearch tool that did the same thing, but with a less obvious name. I think I spent about 2 weeks trying to get good results out of it. Unfortunately, it's really a tool for regression testing new OpenSearch builds. It's of limited use for what I really wanted to use it for. You come ask me afterwards if you want to know about the problems we ran into. So after half-heartedly fighting with this for a couple weeks, I finally got so frustrated I spent an afternoon and wrote a replacement in Go. It really wasn't that hard. Worked beautifully, scaled higher, gave better results, was able to do more testing. It's almost certainly terrible for doing like release regression tests. It worked great for what we wanted it for. So now we had a tool, we could send a flood of varied queries at OpenSearch instance and measure how well it performed under different conditions. What's the latency at low query rates? How does it behave as the load climbs? Where does it break? So now it's time to run a few benchmark runs. So we measured our staging instance. Start with the easiest place. Learned a few things, used that to build a new staging instance and a third staging instance. And then very carefully on off hours, ran a bunch of load tests against prod to get a baseline for how bad things really were. And then we built a clone of prod and ran hundreds of tests, varying different parameters, seeing what happened. We built up a working model of how the system actually behaved and used that to drive more testing. And then the important part is we actually write up the results internally. We tested this, we thought this would help. We did these tests, here are the results. We'd share this around the team, we'd argue about it over Slack, and then do it again the next day, over and over again. So we changed config flags, we changed the number of shards, we changed AWS instance types, we tried different versions of OpenSearch, and none of the things we expected actually made the difference that we expected them to. Almost none of the things. To go faster, we discovered we needed fewer shards of data. We had too many. And reducing that number actually really helped us. Initially, we sharded our data 450 ways. That lots of shards gives you good throughput, in this case, but terrible latency. We only cared about latency. And benchmarks, anything over about 200 shards substantially increased the latency. It just kept curving up. We'd guess it was fan-out costs, extra coordinator load, long tail of waiting for shard number 450 to respond. We shrank to 180 shards for the first round of changes, and that made a nice boost. Picking the right number of shards for all of this is sort of a dark art. Again, feel free to ask me after. But adding new nodes or additional nodes didn't help. We were really only using about 10% of our CPU. Adding more nodes just moved the idle threads around. Most of the config options that particularly AWS had suggested we turn on actually either had no particular benefit to us or hurt. For example, they'd suggested turning on concurrent segment search, which was supposed to help with search parallelism. We had tons of free CPU. Surely parallelizing some of the searches would help. In tests, it cost a few percent right up front. And as the load increased, it just fell off. It never helped us. We didn't find a single workload that it was positive for. We had tons of settings like this. We had to test them all. Somehow, our queries were actually really good, which just shocked me. I actually originally suspected this was our problem, as we were, again, kind of the equivalent of full table scans. OpenSearch's query optimizer was kind of magic and loved our queries. Each shard usually only touched 100 or so documents on disk. It was able to use a bunch of cheap filters that we built to filter down what it should be looking through, did the right thing. It was kind of amazing. It was not at all the result I was expecting. The AWS support people kept claiming their huge wins in every release. We never saw them. We gained a few percent here and there, but nothing major. We rolled through to the most recent release at the time because it didn't have any regressions, and we were going to have to do it eventually. Now, some later testing we did with vector searches had some huge wins after one upgrade, but that's a story for a different day or possibly a different room. Anyway, so swapping for nodes with less CPU and more RAM was probably actually the biggest win. And this is kind of the one that we sort of saw, or at least I sort of saw coming. This is the big issue for us. At the time, AWS had something like 139 choices for different instance types for OpenSearch. After throwing out all the legacy options, we're still left with this huge pile of choices. You know, what ratio of CPU to RAM do we want? Do we want more, fewer larger nodes, more smaller nodes? Well, we could test that. We were able to change to an instance type that gave us 3 times as much RAM, but a third of the CPU for about half the price per node. It actually was substantially faster. And one of the things that we discovered along the way is that even tiny numbers of disk reads had a huge impact on our search latency. This historically shouldn't have been surprising, but pretty much our entire search index had to live in Linux's disk cache because we were running OpenSearch, as is the default, with our storage on EBS, and EBS has terrible latency, even with SSDs. It's not unique to Amazon or EBS. I work on Google's equivalent. It's a fundamental problem to complicated storage layers. So it turns out that throwing RAM at the problem is really the only big obvious win that we would have seen coming. And after looking back, a lot of the outages we'd seen were at least partially caused by cache miss problems. Things got loaded, the cache hit ratio fell, the total I/O skyrocketed, queries started taking long enough that they didn't finish before timing out. Everyone knows the story. So we rolled all of that out. Fewer shards, different instance types, newer OpenSearch release, a couple minor flag tweaks that we knew were safe. We wouldn't have been able to do any of this safely if we hadn't put together a good testing framework. And we wouldn't have known if it worked without all the monitoring work that went in at the beginning. It was a good start. We chopped our budget in half, roughly. Our latency went down, errors fell, timeouts fell, but we're just getting started here. So one of the things we learned was about a third of our user visible search latency actually came from OpenSearch. And Amdahl's law, as we keep speeding that up, there's a limit to how much of a benefit we can get. Another third was spent building the queries, and the last third was spent verifying permissions on each result. The last thing we want to do is have your competitor's documents show up in your search. So, well, a couple members of the team went through all of the data that we had from this, and one of the big performance problems we had was actually kind of this gnarly platform problem with Active Record that no one had noticed in over a year. When we fixed it, the entire company got 20 to 50 milliseconds faster. And it unblocked a bunch of multi-threading work that we'd implemented, but it had never been a latency win for some reason. Well, now it was. So that was fun. We got a bunch of extra performance out of it, out of some code changes this unblocked. Going into this, we suspected one of our problems was that we had too much useless data in our search indexes. We knew we had data in there that was never really being used for searching or was only in corner cases being used, and we were carrying around a ton of additional data. We knew that, but we didn't really know what it cost us, and nobody wanted to make complicated changes blindly. We had no way to know any change we made to our search data took, at the time, months to really get to know how well that was impacting user search. So now we're at a point where we could actually test some of this. We were able to remove kind of the least contentious bit of data from our search indexes, reduce their size by 50%. That gave us another big speed up. Everything was faster. And even better, the latency variance between peak and off peak started to close up. We were doing effectively no disk reads once things were loaded. Everything sat in memory. And we went back to the drawing board and went through and crossed out everything that we didn't need and ran a bunch more tests and lopped another 90% off the size of our search indexes. There was some stuff in there that was almost never useful. We were able to reshard down to even fewer shards. Everything was beautiful. We lopped the number of search nodes down pretty substantially and had this tiny little latency bump when we went from like 60 nodes to 15 or 20 at the end. Things are starting to look good. And I don't just mean for searches. Anyone who's ever talked to anyone from Google, search latency is almost this religious topic. In this case, iteration speed is really kind of what I mean. When we first started, it took forever to run experiments. It took weeks to turn up test clusters. It took months to run different indexing tests. And over time, we were able to speed all of that up dramatically so we could really test things, get an answer, and decide what to do. Sometimes in hours, sometimes in days, never weeks or months. And without that, we wouldn't be able to move forward. You really need to be able to understand the risk and reward from changes. And once you understand that, you can sell this to management, you can convince everyone of this, moving forward is easy. So, not everything was rosy. Some things didn't work out quite like we'd expected, and I don't mean failed experiments, that's par for the course. There are some things we'd expected to be helpful that weren't. Weirdly, asking for help was almost never useful. We spent a lot of time talking to our frontline AWS support people who talked to the people, then we sat in meetings with some of the experts who pulled in a bunch of the developers. And we got a ton of suggestions out of them, but when we tested them, very few of them actually worked for our situation. So the problem is that OpenSearch is used for a ton of different uses. We were using it for document search. We have a bunch of documents, please find the ones that are the best fit for what this user is looking for. It gets a ton of use for log-like uses. People pour their logs into it and then have search on top of it to try to find a needle in a haystack. It gets a lot of use, as I'm sure a lot of you know, trace metric observability platform. And a lot of the AI and vector search stuff is also popping up really big over there. And they're all different with different needs. Most of the older docs we found were really focused on logging and log-like search. And for that, add more shards, add more disk bandwidth, it gets faster. Latency? Why do you care about latency searching your logs? So a lot of the things we were getting, finding stuff online, searching for, talking to their developers, we were getting suggestions on, add more shards, do this. They were the exact opposite of what we actually ended up having to do once we had data to back it. A lot of the newer docs are AI-based, totally different tuning. For us, the single biggest thing was get rid of shards. We had too many, get rid of data after that, and throw as much RAM as we possibly can at it. A few kind of generic pain points of obligatory SRE rant. Possibly my biggest source of pain was other people's dashboards. People built dashboards, they're for the wrong problems, or at least not my problems. And I could, like most people here, probably rant about what makes a good dashboard for hours. But fundamentally, a monitoring dashboard is a communication tool. It's there to tell a story about your service. It's really nice if it tells a true story about your service. But the story shouldn't be, there are 300 different things going on, scroll around for a while. The story shouldn't be, we picked 35 different units of measure for the same thing. And you can make a lot of progress really just by focusing on SLOs, which is sort of the first thing we did here. Even if they're just informal, what matters to the users? Start there. Make sure you have graphs of those. What secondary things impact those? Add some graphs for those. Are there some things that impact those that fit in? Focus is the key. And the other thing that every time I do this, it surprises me, is how terrible monitoring tools usually are at actual data analysis. Try plotting query latency versus disk IOPS rates over all of your instances for a week sometime. Get a scatter plot or a heat map. Sometimes you just have to export your data and use different tools. Google's Borgmon and Monarch at Google were terrible for that. Datadog was terrible for it. Grafana mostly can pull it off. And then the black box that is software as a service is really painful at times, but it's what it is. So kind of wrap up with a few concrete recommendations. If you're running Open and Elasticsearch and you came here because you wanted some recommendations from people how to make it go faster, keep a close eye on IOPS and how much disk, how much it's reading from disk. Keep your indexes as small as possible. If latency matters, keep your shard count small, and make sure your shards are evenly distributed across all the nodes. That is where the dark art of shard sizing kind of comes in, unfortunately. For everything, run experiments, measure things, write up and share your results, and SLOs are basically magic. They make you write down what you care about and discuss it with your whole team, and that's it. That's the whole magic. It lets you focus on what's important, and just because it's simple doesn't mean it's not magic. Thanks. Questions?